So next lecture onward, our video technology is going to change substantially. From the next class, I will no longer be in the video. You will only get something like a screen and icons and things like that. So it will be something more like a Khan Academy video rather than. So now we were talking about in the last class about hypothesis testing. So how many of you guys remember what we did in the last class? You do?
I can just tell you the formula.
That's the basic idea. So we were talking about, everybody remembers what's a standard normal distribution? What's a standard normal distribution?
Zero standard.
So it's a normal distribution. X is normally distributed mean 0 and standard deviation 1. That's a standard normal. Now the second point that's important from the last class is, if you take any random variable x, which is normally distributed with mean mu and variance sigma square, then x minus mu by sigma becomes the standard normal. Do you remember this?
Yes.
So if you take a normally distributed random variable, subtract from its mean and divide by the standard deviation, you get a standard normal variable. Clear? Okay. Now the third point, which we can go over if you've not clearly understood the point, is the following one. If x1, x2, xn follow whatever distribution with mean mu and variance sigma square, then we argued in the last class that x bar is approximately normally distributed. Right?
Is the number of samples we need criteria here?
X bar is approximately normally distributed. Not number of samples. Please do not say number of samples. Say number of sample points. Number of sample points is different from number of samples. That's very loose kind of, right? So, yes, X bar is approximately normally distributed, with the approximation getting better and better and better as n becomes larger and larger and larger. With approximation as n.
That's law of large numbers.
That's the central limit. The law of large numbers says that x bar will get closer and closer to expectation x as the sample size becomes large. That is the law of large numbers. The central limit theorem is about the distribution of x bar. The central limit theorem is about the distribution of x bar.
That you have shown on R that day.
That actually which I showed on R that day. Right? Okay? Sure. The second thing that we know is x bar therefore is approximately normally distributed with mean mu and variance sigma square upon n. Is this idea clear? Does everyone remember why expectation of x bar is equal to mu and why variance of x bar is equal to sigma square upon n? Do you guys remember this?
Yes.
Can you derive this? If I ask you to? How many of you can and how many of you can't? The camera is pointing this way, so you can. But I've got another one. Right? Okay? So how many of you can derive this? Only one? Because you are learning it again the second time in the science class. So can Ankita, so let's go over it again. Right? Okay, so think of So think of x1 xn. This is a sample which is coming from a population. Let us say that the population has a mean mu and a variance sigma square, right? And this is a random sample of individuals from this population. What is the size of the random sample? Small n, right? Size of the random sample is small n. Okay. Now, everybody understands why x bar, which is summation xi upon n, is a random variable.
Yes.
Why?
It is the mean of a randomly picked sample.
It is a mean of a randomly picked sample, right? So the value that x bar takes, the particular value that x bar takes, is an outcome of a chance experiment. If you choose a different x bar, different set of sample points for the same sample size, different set of sample points, then you get a different x bar, right? So it has a probability distribution. What we want to do is, we want to find out what is the mean of x bar. What is the mean of x bar? Expectation x bar, right? Which is expectation summation xi upon n, right? Which is expectation of x1 upon n, x2 upon n, yeah? Right? Alright? This can be written as yeah? Now, the key point is to understand what is expectation x1. The key point is to understand what is expectation x1. What do you mean by expectation x1?
The probability of getting
No. Expectation not a probability.
it's average of a number. So average
Is the average of x1.
which is a number.
Yeah, but x1, what do you mean by x1? x1 is the first value of the first element of the sample chosen.
Yes, constant.
It's not a constant. It's actually a random variable. Because suppose if I I'm looking at a sample of 100 households. I'm conducting a survey on household incomes. I've taken this random sample from all of Mumbai. And suppose the first person chosen happens to be Ankita. So I ask Ankita what's her income and I get a certain figure. But the number that they've gotten as a response from Ankita is a random variable. Because I got that number because I had chosen Ankita. If I had chosen Aniket, I would have got another number. If I had chosen Akhlaq, I would have got another number. Right? So therefore the first number chosen is a random variable. So when I'm asking you what is the expected value of x1, x1 no, x1 is just an arithmetic average. No? I'm asking you what would be the average value of all the of the first number chosen as the sample size becomes very large.
So this would be the expectation itself.
It will be mu.
Yeah.
Because any number can be the first number.
It should be.
Right? So therefore this becomes, this if you understand this idea, it's good. So this becomes mu. What do you think about expectation x2? Mu. Perfect. Like that. So what do I have? N times 1 upon mu is mu. Right? So expectation x bar is mu. On an average, therefore x bar equals mu. Right? So we say that x bar is an unbiased estimator of mu. X bar, the sample mean, is an unbiased estimator of the population mean, because if I take a large, if basically what it means is, even if I take a small sample of size n, and if I get an x bar, and if I use that x bar as a guess for the population mean, I will not get an exact number. My x bar will not be exactly equal to mu. There will be some difference between x bar and mu. But the average value of the difference will be 0. On an average, if I kept on taking many such small samples and finding x bar from them, and if I averaged across all x bars, I will get mu. That's what this means. Which means that the difference between x bar and mu that I get in any particular case is not a systematic difference. So my errors are unsystematic. So my guess is average, is correct on average. Right? So how does it help? Obviously I am not going to take many samples and average them to know what mu is. I just have one sample. But this gives me the confidence that my mistake that I am making is a pure statistical mistake. It's a mistake out of a pure statistical discrepancy which is there between x bar and mu. It is not a systematic mistake. So I am not systematically underestimating mu or systematically overestimating mu. My difference between my estimate and mu is a purely random number which is essentially inherent in the chance experiment, because my x bar is an outcome of a chance experiment. Right? Which is different from saying that my x bar systematically overestimates or systematically underestimates mu. Right? Okay. So let me ask you a question, guys. Suppose I have got 20 observations. Okay? 20 observations. And suppose while entering data, I miss out one observation. Right? Aniket walks into the room, I look at him, I miss one observation. Right? But I don't realize this. I divide by 20. So I've lost one observation. Right? So I'll call this x bar dash, which is summation xi, I goes from 1 to 19 upon 20. Is this an unbiased estimate? Tell me what will be the properties of this. I use this x bar as a guess of mu. Tell me what the bias will be. Do it mathematically. So it is 1 upon 20 into x1 plus 1 upon 20 into x2 plus 1 upon 20 into x19. That is x bar, right? So what is the expected value of x bar? 1 upon 20 expectation x1 plus 1 upon 20 expectation x2 plus 1 upon 20 expectation x19. Right? Okay. So now how many expectation x1 is mu? But how many mu's will I have here? 19. So it will be 19 upon 20 mu. So as she correctly says, it will underestimate. Right? It will underestimate. Right? In general, this will be equal to n minus 1 upon n mu. Right? Now see the important part. This is n upon n mu minus 1 upon n mu. Right? Which is mu minus 1 upon n. So if mu is positive, this will underestimate. If mu is negative, this will overestimate. If you miss out one observation, right, the whole idea will overestimate or underestimate mu depending upon what the actual mu is, and you never know. But there is a saving grace. Suppose I keep on entering. So somebody says, there I have got more observations and more observations and more observations. So more and more observations keep on coming in. So I have got say 5,000 observations now. Rest of the observations I input correctly. I don't miss out. Suppose the remaining observations I input correctly. What do you think will be the impact on x bar as an estimator for me?
If n is large, then it will be negligible.
As n tends, see, so what is the bias? The bias is, this is the bias term, no? As n becomes very large, this will keep on becoming smaller and smaller and smaller. And the impact of missing out that one observation will eventually vanish. Right? But it will never become zero. So even if you really keep on increasing number of observations, you really won't have an unbiased estimator ever. Because you'll always have an underestimation, overestimation because you have lost that observation. Then bias can be made smaller and smaller and smaller by increasing the number of observations. Yeah? But it will never really go up. Therefore, it's critically important to be very sure that you are entering all your data correctly. Right? Okay? Sure. Now, let me ask you another question. So now,
So you can take denominator as 19.
yeah, but you didn't realize that, no? I was talking to Aniket. If I realized that I just missed out one observation, then I will take the denominator 19. But the whole point is that when I was talking to Aniket, I didn't realize that I missed one observation. Right? And if I miss out like an observation, so therefore it's important that when you are entering data in Excel, never talk to anyone. Yeah? Okay. Now let me ask you a question. Okay, how this is useful. Suppose I find, say, my idea is to suppose think of a town. Okay, in that town, all the taxis are numbered 1, 2, 3, 4, 5 and so on. So the first cab in the town is numbered 1. They don't have image like that, right? 1, 2, 3, 4, 5, 6. And then there's a town square. Yeah? This is town square. Right? And the town square, all taxis pass randomly. So think of think of this town square as a cube, and there are all these gas molecules which are moving randomly, right, in grounded motion. So you have taxis moving around here, right? I ask you to estimate the number of taxis in the town. I give you a day. You have to go and sit in this town for a day and estimate the total number of taxis. Yeah? Estimate the total number of taxis. Right? So I send, say Amol. Amol sits there and comes back.
Total number of taxis or total number of taxis passing through the square?
All taxis are going to randomly pass through the square. So taxis are generally passing randomly. Okay, there is a same, there is the probability that a given taxi will pass through that square on a given day is the same for all taxis. So it's not that there are some taxis which are not going to pass through the square. Okay, it's not that there is no, that some taxis are not going to, there is no sample selection. There is no sample selection bias. All taxis are, there is the same probability that any given taxi will pass through the square. It doesn't mean all taxis will necessarily pass through the square on a given day. Some might pass, some might not pass. But taxis are moving randomly. Right? Okay.
Are they going to pass anything?
Pardon?
I mean,
They might pass multiple times. They might pass multiple times. So Aniket comes and tells me that there are 340, my estimate of the number of taxis in this town is 340. I ask him why. Because he says, I was noting down the number, and the highest number that I saw on the number plate is my estimate of the total number of taxis. Because I didn't see 341, taxi number 341. The highest number that I saw was 340 on this today. So 340 is my estimate of the number of taxis in the city. Right? So what Aniket is doing is, Aniket is using as an estimator, so let mu be an estimator that I want of the total number of taxis in the city, and the actual number mu is the total actual number of taxis, and Aniket has created for me an estimate mu dash. What is Aniket's rule? If Aniket, this is Aniket's sample, x1, x2, x3, xn. These are the numbers that Aniket saw. And Aniket's estimate, mu dash or mu hat, is the maximum of this. Right? Because he says the highest number that I saw on the number plate of 340. So there must be 340 taxis. What do you think? Will this be an unbiased estimate? So if somebody were to, obviously, Aniket, so the question that I'm asking is not whether there are exactly 340 taxis in the city, but the question I'm asking you is, if Aniket replicated this every day, will he be correct on an average?
If he doesn't miss out on observation, he will.
Yeah, suppose he doesn't miss out any observation. Aniket uses this route, that he is going to choose as an estimator of the number of taxis, the highest number that he sees to. And I don't expect him to be correct on any single day. I want to see if this rule is generally used. Will you be correct on an average? Some days I might underestimate, some days I might overestimate. I am perfectly fine with that. It's an estimate. Alright? Okay? But I want to be correct on an average. I want to be correct on an average. Yeah?
It will be correct if he is every of the day. Then we keep it low.
He said it will be correct on it. It's like, when I was a college student, there was a very popular restaurant that all of us went to in Pune, Deccan Gymkhana. The owner of the restaurant was totally blind. So when he used to buy milk, so whenever that time milk used to come in those liter bottles. So he used to weigh bottles like this. Right, and sometimes of course he would think that this is not 1 liter, but on an average he was right. He would get, on an average his estimate would be correct. Sometimes he would underestimate, sometimes he would overestimate, sometimes he would say this is less than a liter, sometimes say more than a liter. But his sense, so that is exactly what's happening. Right, so can you tell me whether Aniket will be right? Yeah? He'll be right?
If the number of days he observed is quite large.
So you think, so each day the estimate that he gets. So what we are trying to look at is whether, the question that we are asking is whether expectation you had is equal to you. Right? Okay? Okay. Now, suppose indeed the actual number of taxis in the city is capital N. Okay, so let's try to understand this problem properly. The actual number of taxis in the city, let's call it capital N. Say 7,000. So capital N is 7,000. You have taxis number 1, 2, 3, 4, 5 up to capital N. Right? Sure? Aniket is likely to observe any of those on any given day. Right? So effectively what happens is, what Aniket is observing is so think of what Aniket is observing is a random variable. The number that Aniket observes is a random variable. Right? Sure? Okay. So, and he is going to observe each number, any of these numbers with the same probability because taxis are going to the square the same probability. Right? So therefore his observation is a random variable distributed between 1 and n with the probability 1 upon n. You see this point? Right, so each has the same probability of occurring. Right? Each has the same probability of occurring. Sure?
Flipping a coin, you have only two.
Yeah, or
Exactly.
rolling a die.
Yeah.
Suppose, so look at it. It's very identical to actual rolling a die. You're rolling a die. The die rolls 1, 2, 3, 4, 5, 6. So suppose you have not seen the number on, you do not know that the highest number on the die is 6. I keep on rolling the die. You have to tell me what is the estimate of the highest side on the die. So if you see 3 on a day, you say it's 3. If you see 2 on a day, you say it's 2. If you say 6 on a day, you say it's 6. I am asking you whether you will be correct on an average. That's the same problem that we are getting here. Right? So think of a die. When you do this on a die, you have 1 to 6. And what you observe as the same probability of occurring as probability 1 by 6. So what you are observing is 1, 2, 3, 4, 5, 6. Right? So what you are going to observe is 1, 2, 3, 4, 5, 6, x, probability of x, 1 upon 6, 1 upon 6, 1 upon 6, 1 upon 6, 1 upon 6. Right? What is the expected value? So your estimate is this. Sometimes your estimate is 1, sometimes your estimate is 2, sometimes your estimate is 3, 4, 5, 6. What is the expected value of this? 3.5. But what is the total number? What is the highest number? 6. So is this an unbiased estimate? on an average, you will get your estimate will be 3.5, but the actual value is 6. In general, if this is 1, this is n, the expected value of mu dash will be n plus 1 upon 2.
So, but here we don't know that there are n gaps.
Yeah, but that's precisely. Suppose when you're rolling a die, suppose I told you that you don't know the last side,
Yeah,
6.
6. We don't know.
You don't know 6. So every day you see whatever number comes up, you tell me that is the maximum. I keep on rolling the die. The maximum that you see on the side, suppose you rolled it 15 times, you see the maximum number that is occurred is 6, so you say 6 is the highest.
115 we do that now.
6 is the. But that's exactly what you're doing for the taxi. Right? So someday your maximum that you see could be 6, someday the maximum you could see could be 3, someday the maximum you could see could be 2, someday the maximum you could see is 1. The point is 1, 2, 3, 4, 5, 6 are likely to be observed with equal probability. So the expected value of your guess will be 6 plus 1 upon 2. Or in general, if n is the actual number of taxis, on your average answer will be n plus 1 upon 2. So you will actually significantly underestimate. But suppose you do the following. You say 2 mu dash minus 1. So you say what I am going to do is, whatever number Aniket tells me, Aniket has seen taxi number 700 today, which is the highest estimate. So I said multiplied by 2 makes it 1400 minus 1, 1399, and then I create a new estimate. Will that new estimate be an unbiased estimate? So look at it this way. Okay. 2 mu dash minus 1. That's my estimate. So what is the expected value of this? Expected 2 mu dash minus 1 is 2 into minus 1, right? Yeah?